give it a few seconds to allow people into the room.
Okay. So we're now live.
Hi, everyone. Welcome to the opening keynote of Quantum Tech 2021. It's a pleasure to have you all here, as you heard me say a few minutes ago. And I'm delighted to introduce Carl Williams as our opening keynote. Carl is the acting director of the Physical Measurement Lab at NIST and leads the NIST Quantum Information Program. He also co-chairs the Quantum Information Science Subcommittee of the National Science and Technology Council, and I'm really looking forward to hearing his thoughts on near-term commercial applications of quantum technologies. As I mentioned before, you can please submit your questions via the chat function, and I'll be fielding those to Carl towards the end of his presentation. But yes, please sit back and enjoy. And Carl, the floor is yours.
Thank you, Amit. It is a pleasure being back at Quantum Tech. I wish I was there virtually, not virtually, was there in person so I could engage with you in real time before and after presentations. But with COVID, we will have to continue to operate this way. So I'm going to talk about near-term commercial applications of quantum technology in the sensing, imaging, and metrology area. And so let me first start out as a keynote of what I consider what is quantum information. And for those of you who are not really well aware of this field, it really is moving from the quantum technology that was used in the 20th century, things like transistors and lasers that basically use the semi-classical properties of quantum mechanics, to using the real exotic properties of quantum mechanics, the pieces that Einstein found so strange that he spent half his career trying to prove quantum mechanics incomplete. The fact that an electron can go through two slits simultaneously, and that you can prove that it has gone through both, that it's really a wave and a particle. I like this quote on what quantum information is, in part because it is very descriptive without actually having anything wrong in it. Quantum information is a radical departure in information technology, more fundamentally different from current technology than the digital computer is from the abacus. Another way of looking at it is as convergent of two of the 20th century's great revolutions. A convergence of quantum mechanics, which was born at the end of the 19th and beginning of the 20th century, and information science, which really came out as purely a theory before the physics of information science was put underneath it. And when you merge these two together, you get a new science that really gives rise to what I will call the second quantum revolution. So quantum information science exploits unique quantum properties such as coherence, superposition, entanglement, and squeezing to acquire, transmit, and process information in ways that greatly exceed existing capabilities. It is a field of scientific inquiry in its own right. It is developing to an engineering field as the technology progresses. It has applications in sensing, metrology, which we will talk about primarily in this talk, communication, simulations, computing, and robust intellectual connections to numerous areas of basic research. And the programs at NIST really cover all the space. So what is the timeline for it? And the timeline is really quite long. And so I want to talk about this for just a few minutes. In this plot, I show difficult complexity. Take that as some product of the number of qubits and the number of operations you must do in order to do a computation or to process or to do something specific. And years. Well, clearly quantum computation and quantum networks are the things that's going to take the longest to develop. There's probably so much we do not yet understand about what we're going to do because of many things we have not thought about. So the things in red are kind of the things that are a little exotic. Today, you can go buy a quantum key distribution system. Quantum measurements are available. In fact, they are used for some of the most hardest computations around, calculations around, such as clocks, but usually only at the most sophisticated labs. Quantum sensors are emerging. And we're going to talk a lot about those today. I have this thing called quantum network relativistic geodesy. And how do you use a quantum network to do relativistic geodesy? To look at the modes of the Earth, breathing, and perhaps at one day in the future be able to tell the stress is building up along the San Andreas Fault, and that we might be able to predict the worst earthquake that's going to ever hit California 2-3 weeks ahead of time. This is the potential of this technology, and a quantum network for relativistic geodesy is nothing but a sensor network, but it is way out because it requires the technology to develop quite a bit. So this is kind of my timeline. Let me come in and talk just a few minutes about NIST and the Physical Measurement Laboratory at NIST. You know, NIST is a National Measurement Institute. It is a place that basically provides the physical measurements for a country. And in NIST, we have two primary locations in Gaithersburg, just outside Washington, D.C., and in Boulder, Colorado, where we make some of the hardest measurements around. And the mission of the Physical Measurement Laboratory at NIST is to set the definitive US standards for nearly every type of measurement, whether we're measuring time, or the volt, or length, or even a gallon of gasoline, or a liter if you happen to be in Europe. And to be a world leader in the science of measurement, always being able to progress this and make better and better measurements, whether at the nanoscale or in gigaparcels. So one of the things that we have done for many, many years now, for more than 70, is build clocks. And the quality of our clocks have improved. The blue dots are basically primary frequency standards, because the second is defined by a microwave transition in cesium. And the red dots are what we can currently do with optical clocks. And you can see since about 2006 or 7 that our optical clocks are actually better frequency references than our microwave clocks. And this will eventually lead to a redefinition of the second sometime in the next 10 years. Now, I mentioned this because all the way back in 2010, one of our optical clocks was called the quantum logic clock. It was an aluminum ion being used as a ticking, and a beryllium ion that controlled it. And since the ion is in an ion trap, you can excite the motion inside that trap. And even though it's not moving that fast, if you look on the left, you can see as you excite it that its frequency was changing. This is just special relativity. Not moving that fast, but I can already see special relativity in my clock all the way back in 2010, just by exciting the motion ever so little. On the right, you see a plot, first with a bunch of blue bars and then with red bars. And what happens? Well, I have my clock sitting on a laser table, and partway through the experiment, I jack the table up 30 centimeters, approximately a foot. And you can see that it ticks at a different frequency. This is general relativity having an impact on my clock because it's now in a different gravitational potential. So more than a decade ago, we could see this in our clocks. Our clocks have improved dramatically in the last decade. But what I'm trying to show you is that all the way back in 2010, my clock was already a sensor of both the velocity of my clock atom and the gravitational field it's set in. Additional standards that we already have and have been using for many years is the Josephson-Volti standard. This is nothing but a bunch of Josephson junctions being driven to provide very precise volts, a volt. And so we put 300,000 of these on a chip. And this is the standard for the volt around the world. And on the right is gallium arsenide quantum Hall effect, realizing the ohm. Again, The Josephson voltage standard is the same technology that is now being used for superconducting quantum computing. So again, these standards have been around for a time. So what I've tried to convince you of is that we have been using quantum properties for many, many years for the most accurate measurements. And they are becoming sensors technology. So if you look around the world, PTB in the United States sell about 70% or 80% of the voltage systems that are used to realize a volt, whether it's in China, Australia, Brazil, or many other places. And the gallium arsenide quantum Hall device is now being replaced by NIST and other NMIs, including NPL and PTB, by graphene quantum Hall devices. And in the future, we might be able to integrate these together into a single instrument and provide fully traceable electrical measurements in an instrument. More than 20 years ago, NIST basically took a Josephson junction quantum Hall device and a single electron transistor and proved that V equals IR. Now, you can say proving Ohm's law is not something anyone should do. But we did this at about 20 parts per billion. That experiment has never been replicated. But this is the principle by which one would build an electrical instrument that would effectively be able to realize all electrical quantities and be absolutely traceable. Back in the early 2000s, we built one of the first high-speed gigahertz QKD systems. And as a result of that, we realized that we needed to build better detectors. And so we went out to build better detectors. And one of those detectors is a transition edge sensor. It has basically near 99% quantum efficiency. And if you put an average mean photon pulse of 4 in there, it will have Poisson statistics because it is a laser. And you can see on that first trace, n equal 1, 2, 3, 4, 4 being the brightest, 5, 6, 7, 8. And you can see that it's satisfying a Poisson distribution. The detector can not only detect the number of photons in a pulse, it can detect and see the distribution completely, totally. So it's a photon number resolving detector. Such technology has also been used in things like the Atacama cosmic microwave background telescope. So let's talk to the type of quantum sensors and their potential applications. And there are a lot of types of quantum sensors and potential applications. From everything from environmental and remote to seismic to magnetic fields, electric fields, gravity, and even exotic things like dark matter. We can talk about bioimaging and MRI, magnetoencephalography, magnetocardiography. Oh, looking at the cosmic microwave background. In vivo optical imaging, because as Bill Phillips would say, if you want more signal, turn up the power. But if you're trying to do this in vivo, turning up the power is cooking your host. So how can I take just what few photons I can get and turn them into an image? Well, I've showed you a detector that does that. Very long baseline interferometry and all kinds of metrology, because as I started, we already do electrical quantities and time, but even this metrology is changing. And I will talk a little bit about that. Now, I don't expect you to read this chart. I am putting a reference to a review article that talks about quantum sensors. It's pretty complete. It shows all the different kinds of quantum devices that can be used for sensor technology, typical frequencies and other things. This is a quite good review article from a few years back. I really encourage those of you who want to know more to go pull this and look at it. I want to come back to an effort that occurred and was first demonstrated back in 2003. And that was taking one of these big atomic clocks that was on a table and turning it into a chip scale device. This was something that was done with DARPA. And we basically miniaturized it. Yes, we lost some accuracy as a result of doing it, but we created the first chip scale clock. Such things now can be used for doing seismic monitoring and other exotic things. So let me go into where this is going and what you're likely to see in the next few years. So a few examples of quantum imaging systems and quantum centers. I'm going to mention a few companies here. Notice these are not endorsements by NIST. They are just examples of companies working in this space so that you can go look and explore and see what's really going on. So that same technology that was used to create an atomic clock, if I put it on a magnetic sensitive transition, it can be used to create technology for mapping the brain. Previously, people who did big needle encephalography would use a superconducting quantum interference device, which requires cooling and everything else. But new technology is emerging, both based on atoms and on nitrogen vacancy centers and diamonds. It is compact and does not require cryogenics, which means that it's more portable and doesn't require as big of a device. And so there are a bunch of companies using this kind of technology, and I'd like to mention just a few of them here. QSpin, working with Mansfield Imaging Center in the UK, has basically demonstrated looking at brainwaves using these very sensitive technologies. There are other companies out there like Kernel, QZaber, QDTI, which stands for Quantum Diamond Technology Incorporated, who are basically using slightly different technology from atoms, but basically building new types of sensors. And if you go out and you search the internet, you will find that there are companies out there that are looking and evaluating the magnetometer market. And again, these are just 3 companies you can go look at talking about what the market is like. Now, the problem is squids, these superconducting quantum interference devices, are very, very good. Displacing that technology is not going to be easy. And we know that displacing technology takes time and effort. But it is occurring, and it is occurring today. Again, coming back to these types of devices, you can build very much larger ones. And what's pictured on the left is a picture of an atom interferometer by Mark Kasevich at his Stanford laboratory. And I should point out that Mark Kasevich is also the chief scientist of AOSense. But he's built one of the world's largest atom interferometers to basically go and verify Einstein's equivalence principle at a level that's previously not been verified. But that, like I said, the same technology on larger scales can be used for gravimeters, gravity gradiometers, precision navigation and timing, and inertial navigation. And there are a large number of companies who have different systems around this. Some of them new startups like Muquans and Vector Atomic, others long existing companies who are pushing the technology farther. And again, Microsemi is there. They're the ones who currently own the chip scale, the CSAC that I showed you earlier. So again, I encourage you to go explore these because these are the companies that are beginning to build out the business cases for quantum sensors. And in the DARPA ACES program, ACES standing for Atomic Clock with Enhanced Stability, there's an effort to build a new chip scale clock with 1,000-fold improvement over the CSAC. And this will use comb technology integrated onto chip with a small rubidium vapor using 2 photon transitions to build the max clock. And people are beginning to explore building a 3U or 2-liter atomic clocks that will even have better stability. So there's a lot going on. And as I said, something that can be used for a clock, if I put it on a magnetic sensitive transition, becomes a magnetometer. And if I move it up and down a gravitational field, I can measure gravity. So again, this technology is really evolving and evolving rapidly, but there's a lot of component technology and capabilities that need to be built out. The quantum supply chain needs to be built. And for those of you who have heard, in the US, we have the Quantum Economic Development Consortium, which is working to help understand the supply chains that will be needed for future technologies, everything from lasers to frequency combs on chips, to small vacuum technology and other things that will allow things to be built small and compact. So now that I've kind of given you some flavor of what's going on in the commercial world, I want to come back to metrology and what's going on in the metrology world, both from a NIST perspective and from a commercial perspective. And again, we talked about the CSAC as the first demonstration, but the CSAC is really the first effort in what we are calling NIST on a chip technology, or NOAC for short. And what is NIST on a chip technology? Well, it's an embedded standard, a standard that would be deployable, usable, flexible, and manufacturable. Because at the moment, if you want the best measurements, you send them to a place like NIST, and we calibrate some device for you. And when you need it recalibrated, you send it back to NIST, and it takes time and effort. And we are working to basically move the standards out of our labs directly on to the factory floor or into a car or other device, and to ensure that it is traceable back to the metric system. And for this to be true, it needs to be deployable. It needs to be usable, it needs to be flexible, manufacturable, and have a cost point suitable for its use. Cost point for an automobile is very different for a cost point on say, the floor of Boeing's manufacturing floor where it builds airplanes. So NIST on a chip is basically a suite of quantum-based measurement technologies that's self-calibrating, fit for use, and able to be given to the end user. And so let me talk about some of this technology. Well, there are chip scale devices, and you've seen some of these that are being used now as magnetometers in some of the technologies. There are integrated optical suites, such as cones on chip, the graphene resistance standard, vacuum technology, AC and DC voltage standards, Rydberg atoms being used to measure electric fields, something that we previously never could directly measure. And optomechanics. So where is all this going? Well, it's going a lot of places. It's going to make new devices, and a lot of that technology I just talked about is being commercialized, whether they be photonic thermometers or other things, and put out onto floors where they can be used. But clocks are also continuing to evolve. And so let's talk about what's going to happen at the large scale and how we might get to this point of relativistic geodesy. So in the last few years, our clocks have become increasingly accurate. And today we can create a Fermi degenerate gas and turn it into a clock and show that it scales as 1 over n instead of 1 over square root of n. Show that 2 patches of this clock can actually tick at slightly different rates just because of gravitational potential. So these clocks are becoming increasingly accurate, and within the next few years, will reach levels of precision that may be able to test fundamental physics, including exploring things around quantum gravity, dark matter detection, and long baseline instruments. In the past year at NIST, we have been able to compare 3 of our clocks at a level of accuracy of a few parts in 10 to the 17th, which is far better than we can actually transfer time using our microwave clock. We can take a couple of these combs and we can self-replicate, beat them off each other and create a gigahertz signal that we can count. We can run the clock at a level of precision that is a few parts in 10 to the 18th. and demonstrate it. So if you think out in the future and you think about taking the most accurate clock you can, if I put those out and I have a quantum network and I can entangle them along the San Andreas Fault or on a volcano, I can watch the micromotions building up in the Earth's tectonic plates and maybe be able to predict when that volcano is going to erupt or when the next earthquake is going to occur, saving lives. But to do that, I need to take that technology. I need to make it far more compact. I need to be able to create quantum networks to entangle to these clocks along that baseline. So a lot of work has to go. And it goes back to that first plot I showed of the time scale for this technology building out. Just as the laser and the transistor took 50 years to build out, the kind of quantum devices we will have in 20, 30 years will be very, very different from the ones we have today. And yet we already seen the miniaturization of things for magnetic imaging. And you're going to hear more about that in the talks in this first session. If I take these same clocks and I put them out in space, because a clock on Earth is not very useful, because I've already shown you that a clock on Earth can detect the gravitational field it is. And whereas a decade ago, it was 30 centimeters, today we can see a centimeter. And in the near future, much less than a centimeter. So the best clocks need to go into space. Oh, we already have clocks in space. They're part of the GPS system that allows us to drive with our mobile devices. If I put them at the Lagrange points, I might be able to create a system to look for gravity waves or certain types of dark matter. So networks of clocks and long baseline interferometry can be useful for things like relativistic geodesy, earthquake prediction, volcanic eruptions. They're already used for guiding our cars, but in the future, with the better clocks, looking for dark matter and gravitational waves that can do a lot. And so as I finish, I want to come back to a very interesting story, because it tells you where the technology is going as it becomes more compact, smaller, and cheaper, because it will get used in different ways. So back in 2017, LIGO and Virgo basically saw the merger of two neutron stars, and a number of our telescopes were turned to look at them. I mentioned this because the reevaluation of the data from those telescopes basically detected that in the merger of those neutron stars, we saw the creation, the formation of strontium. And why is strontium so interesting? Well, that Fermi degenerate clock that I showed you from GILA, our laboratory at CU in Colorado, was using strontium. So in some ways, the story has come full circle. Strontium is formed only in the most violent collisions in interstellar space, and is created and being used today to build the world's best atomic clocks. This is a wonderful story. It's a story of where technology is going, of where we will be in the future. And so I encourage you to listen to the session today, to see the talks on magnetometers being used to do brain imaging, because this technology is not only going to improve the quality of life, it's going to help us explore and understand fuller our universe. And it's going to be an exciting time to watch and to go forward. So with that, I'd like to conclude. We are witnessing the second quantum revolution, where technology will use the weird properties of quantum mechanics, this superposition, this entanglement, and will exploit how nature works at the quantum level to build new kinds of devices, including quantum computers. And as Richard Feynman said in 1981, if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And in fact, it has taken us 40 years from the time he said this to show the first simple quantum processors. It is building out and making this technology more robust that will allow sensors to have the most valuable application, to allow NIST on a chip to come into the laboratories and out onto the manufacturing floors and into cars, and perhaps one day allow people to have an instrument in the ambulance or in a bag so somebody can check for a concussion at the site of where the accident occurs instead of having to wait to get to a doctor's office. And why? Well, it is at this level, at the finest level, that quantum mechanics works. And if we can exploit that technology to build better sensors, better imaging systems, and everything else, it will be an exciting world. And we can build all kinds of novel devices, some we probably have not yet even thought of. So with that, I'd like to conclude, and I'm happy to take any questions.
Thank you, Carl. Wonderful talk and such a fascinating field. We have several questions. One which is very pertinent in the world we live in. Are you able to think of applications of quantum technologies to help solve some of the climate-related problems that we see in front of us?
Oh, absolutely. There are a couple of startup companies that are basically using, and again, I always say that quantum-related technologies. I mean, a lot of the technologies going into things like sensors and all the lasers and everything else are really quantum 1.0. But putting them on chips and everything else is what's crucial. And using Duke home spectroscopy, we can now actually detect greenhouse gases, whether it's methane leaking out of a pipeline or leaks on a gas field and everything else. This technology is really becoming quite robust and very, very sensitive. And so the revolution in remote sensing technology, again, another kind of the technology that's being used. It used to be that to calibrate a laser, you absorbed it in water to figure out how much power it was. Today, we reflect it off a mirror and use the photon pressure off the mirror. We basically are weighing the photons so we can actually determine the actual pulse size. Again, this is technology that comes out of things that we've learned about laser cooling and other things. So it's all quantum 1.0, but it's allowing us to build very much more sensitive technology. So absolutely.
Mm-hmm. Another question, how can industrial and commercial players best prepare themselves to capitalize on the coming opportunities presented by quantum sensing?
You know, this is one of these questions which is really very, very, very difficult because it's the chicken and egg problem. And it's always difficult to say. I think what's most important is to engage in things like quantum tech, Q2B, join Quantum Economic Development Consortium, where you can engage with others and figure out what like-minded technologies may be supporting, because understanding whether a technology has multiple applications also tells you how much investment you should make in making it come forward. So the investment decisions are really hard. You know, you can see the companies making the big bets on quantum computers. It's more risky to try to displace existing technology, and part of the problem with quantum sensors is you're really trying to displace existing technology. But I think it's going to happen in part because it's more portable, it can be more compact, and yet you know it's going to take effort, and I think discussing in the broader environment can help companies position themselves.
A question, can quantum clocks, the concept of quantum clocks, can they be utilized in understanding space-time dilation?
So it is believed that, one can do this. The question is can you see the ripples of the fabric of gravitational waves? And part of putting the clocks in space on the long baseline interferometer was that I could go to much lower frequency, which means larger gravitational waves. And the reason I can do that is just because of the long baseline. And again, most of the big objects in space that are colliding are probably far larger black holes than we can detect today. So yeah, dilation does it point to a violation of how gravity and quantum mechanics come together? Yes, in principle it can. Again, the experiments like Mark Kasevich are doing can do that. So absolutely.
And Carl, you mentioned in your presentation the broader supply chain and enabling technologies and the development of that infrastructure. Where do you see the key gaps, certainly in the US, in that broader enabling supply chain? And what can we do to sort of encourage and foster growth in that?
Well, I think there are numerous gaps, and so I'll point out two of them. Both of these come from studies that have been done by the QEDC. In one, we had a look at laser technology for quantum, and part of this was when is it worth investing the hundreds of millions of dollars to drive a laser technology to become very cheap? And we've done this. I mean, telecom lasers are very, very cheap and quite good. The lasers that are sitting in your Blu-ray player at home are very cheap and quite good. We can drive them. And when we start looking at all the different needs, the question is what is the market? Because how much I want to invest and how much I want to drive the price down depends on the size of the market. And so they're trying to build a tool that will help look at the broader markets, so people and companies can begin to understand where there's enough of a market pool to drive an investment. So that's one example. The second one was we looked at cryogenic technology. And again, superconducting quantum computers, quantum dots all require these dilution refrigerators, very, very low temperature cryogenic systems. And if that cryogenic system costs $600,000 a pop, it cannot be used for a quantum repeater every 50 kilometers along the internet. So how do I build better cryogenic technology? And so we have explored that and are beginning to explore some things. I think there are many technologies, because again, if one goes back and looks at all the supporting technologies for the semiconductor industry, it's just massive. I mean, it's not one company, it's hundreds of companies who support that full infrastructure. And so building out all the quantum technology is going to really take a long time and require building out a supply chain quite different from what we currently have.
Mm-hmm, mm-hmm. Absolutely, and I think that the promise of building a new industry, a nascent industry, a real growth opportunity for economies around the world as we come out of COVID. Again, Carl, thank you so much for setting the scene for the next couple of days. Always a pleasure to have you at Quantum Tech, and thank you for your insights.
Thank you, Amit. I truly appreciate it. Bye.